Hello, everyone, and welcome to another session of chemistry learning fun. Our focus today is going to continue to learn more about solutions. As it notes, if you haven't watched the Zoom meeting from day 4, unit 10, please go back and watch that. It gives you some context for something that will be super important for this lecture. Let's get into it. Today, our objective is going to be focusing on something called vapor pressure and osmotic pressure, melting point and boiling point, compared to a solution compared to a solvent. So the idea is how might those properties change when instead of just having a pure solvent, you have something dissolved into it. So kind of a bulky EQ, but you can separate it if you want to, or you can make it into one kind of long one. That's fine, whichever makes sense to you. But the whole point is that EQ will give you a guide of what you should know by the time we are done with these video notes. All right, let's get into it. So what we're learning about today collectively is known as colligative properties. And the definition of that is properties of a solution which depend on the concentration rather than just the identity of it. So that's kind of a new sort of thing. So for example, if we have two solutions, one of them is potassium chromate and the other one is calcium chloride. The idea is if they're both the same molarity, they would have the exact same colligative properties, the things we're going to focus on today. So even though they look different, they're made of different things, the fact that they're both 0.1 molarity means that they could have the same colligative properties. And Beaker is amazed at that, and maybe you are too. But that's what we're going to focus on. So again, it's not the identity of the particles, it's how many particles are there. And that's kind of a big deal. So go ahead and just process that definition so far, whether you rewrite it or fill in the blank or just something really specific about just this definition of colligative properties, because that is what we're going to focus on for the rest of our video lecture. Okay, the first colligative property we're going to talk about is vapor pressure lowering. So spoiler alert, literally there's no secret. The vapor pressure is going to be lower if you have a solution compared to a solvent. So first of all, we just review what vapor pressure is. We did it in the bell ringer, but that wasn't part of our notes. So let's just make sure that's super clear. Vapor pressure is the gas pressure above a solution due to the solvent particles that have been evaporating. And then again, it tells you right away that the vapor pressure is going to be lower. Well, let's think about why that would be. Like, why is it automatically? I don't have to measure it or predict it. It is. It's always going to be some amount lower. Well, why is that? Well, remember that the solvent particles have to be able to evaporate. But if they are in a solution, that means that they are interacting with the solute particles. And the reason the solute was able to dissolve is because they were attracted to each other. So if you have pure solvent, the water is just attracted to all the other water particles, and it will leave when it has enough energy. But if you have an aqueous solution, the water is attracted now to each other, but also to whatever that solute is. And so if the solvent is attracted to the solute, which we know it is because otherwise the solute would not have dissolved, that means that less of the solvent wants to leave. It doesn't want to leave behind the solute. It's attracted to it, right? It wants to stay with it. And then it's less likely to turn into a vapor. So vapor pressure will always be lower for a solution than if you have a solvent. All right, so that's our first colligative property. And so that one we're just going to do qualitative. So I could ask you questions about, what would happen if you have a solute compared to a solution, or solvent compared to a solution, which one would boil at a higher temperature, those kinds of things, but not an actual calculation. The other colligative properties we're going to talk about today will involve actual calculation. So the second one I want to talk about is osmotic pressure. Now, it's possible you recognize osmotic as the term related to the term osmosis. And just remember that osmosis is a process, so something moving, something happening, where a solvent can go through a permeable membrane. The solute is not able to move through that membrane, but a solvent can. So here would be a visual example. Just so you know, this is the original YouTube. Okay, so you've got some sort of solute in here, some sort of solute in here, and water is the solvent able to move through. And so in this case, here was the original, and then here was after osmosis happened. So the water level you can see changed. So the water moved through the semi-permeable membrane, and then the solute didn't change, like 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. But let's think about what that does to the solution. You now have less water, same solute. So that means, think about it, the concentration got Higher, yep. Now this one, you have more solvent and the same solute, so this concentration got lower. So the idea here is that this happens in food hydration, it happens in, or dehydration, it happens in plant cells, in people cells. It's part of what happens with your like fingers getting kind of pruny when they're in water too long. So this idea where water can move, or solvent, but specifically water in lots of places, can move through a permeable membrane, but other things cannot, is actually something that happens a lot in our world, osmosis. Okay, but a term was osmotic pressure. So osmotic pressure is the pressure needed to keep osmosis from happening. So for example, if this was some type of system like being represented in a cell or some sort of machine or lab thing, and I did not want this to happen, I did not want this to happen, I didn't want the water to move through, how much pressure would need to be right here so that the water cannot move through it? That's what osmotic pressure is. You could also think of it as the other way. Well, what if I want there to be osmosis? How much pressure would the solvent need to overcome to let osmosis happen? So it's the same kind of thing. So how much pressure would need to be inside the cell to be able to push through if there was osmotic pressure outside? Or how much pressure would I have to add to something so that osmosis can't happen, so that the solvent will not move? That's the idea. Now this one we are going to do quantitatively. So the equation is the symbol pi, not as in 3.14 pi in math, but just the symbol pi equals capital MRT. Okay, now maybe this sounds kind of familiar, but let's review what that capital M is. Remember that capital M is moles per volume, and possibly remember from once upon a time, we learned that the symbol for moles is often N. So really this is like N over V. R and T, and then we said pi is pressure, P. So maybe you recognize, oh, this is kind of similar to that Pervnerd equation, PEV equals nRT, right? Because if we're solving for pressure, which is pi, V would have to divide. Well, if I divide N, which is moles, divided by V volume, you get molarity. So that's where that comes from. So just to review, make sure we know what all the symbols mean. So pi is your osmotic pressure, and it's going to be measured in ATM. Capital M is molarity, and that's going to be measured in moles per liter. R is a constant. Remember, was this some guy, blah, 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 Rulberg, that did a whole bunch of work and figured out the liters in atmosphere over mole Kelvin. Those are the units of this R constant. So remember, this whole thing gets plugged into R, and then that will cancel units that we don't want. And then T, remember, is temperature, but it does have to be in Kelvin. Why? Well, because the units of R have Kelvin in them. Generally, you're going to be given a temperature in Celsius. So just to review, you take 273 plus your Celsius, and then that turns it into Kelvin. So that's kind of the idea of this equation. So pi equals MRT. Pi is pressure, osmotic pressure. M is molarity. R is a constant. You plug in this whole thing, and then T is your temperature. But remember, it does have to be in Kelvin. Okay, well, let's see an application of this. Like, what would this look like? So I actually have a real life example. So people that cure meats, which is a preservation process, the reason that curing meat helps them last longer is because the salt, generally that's what you do when you cure meat, you just put it in a lots of salt solution. And then what happens is the salt draws the water out of the microorganisms. So like whatever raw meat you had, there's organisms that are living there. And if there's enough of them, that's when it would start to rot, or we would get sick if we would eat it. But if you surround this thing with salt or a salt solution, what happens is the salt, the water from inside the microorganisms wants to dilute the salt solution that you've put it in. So the water leaves, it goes through osmosis so that it will go into that salt solution. But the tricky thing is we don't want the water to go back into the microorganism. So typically, you can do this with about 20 grams of salt and 100 milliliters of solution using water, and generally a little bit warmer than room temperature, so 28 degrees. So then the thing is we would want to have this in a pressurized situation so that the water doesn't go back into the microorganisms. So we want there to be enough pressure so that osmosis cannot happen and go back into the microorganism. So that's my application question. Well, let's figure this out. We're using, it's asking for osmotic pressure. So we're using this new equation, pi equals MRT. And then if you look at the data that we have, M is molarity, R is a constant, T is temperature, we can solve this problem. So let's pare it down. So 20 grams of salt in 100 milliliters of solution, 28 degrees, I'm solving for osmotic pressure. So first, let's go with molarity. We need to have the moles per liter. Well, we're given grams and milliliters. Well, by salt here, they do just mean table salt, sodium chloride. So I can figure out the molar mass of salt, and I can go from grams to moles. So 20 grams of sodium chloride, this is the molar mass added up. So 1 sodium, 1 chlorine added up, that's the grams per mole. Grams will cancel, and I'll get the moles for the top part of my molarity. The liters of solution, well, I have milliliters of solution. So if I take 100 milliliters divided by 1,000 milliliters times 1 liter, that will give me my amount of liters and my amount of moles. And notice I didn't worry about sig figs yet because we're not at our final answer. So if I divide this out, that will give me somewhere around 3.4 molarity. All right, so then that's my capital M. Now I need to have my R. Remember, that's a constant, so 0.0821 liter atmosphere on the top, mole Kelvin on the bottom. Those are the units. This whole thing gets plugged into R. And then temperature says it's at 28 degrees, but that's in Celsius. And remember, we need Kelvin to cancel. So I'm going to take the 28 degrees Celsius plus the 273. That will turn it into 301 Kelvin. All right, well then here's my equation. I've got everything. MRT, I can plug it in. Pi, or osmotic pressure, equals 3.4 molarity times the R value, which is 0.0821 liter atmosphere over mole Kelvin, times your temperature, which is 301 K. Well, let's check our units. Remember, molarity is really moles over liter. So look at moles and liter. Moles is on top, here moles is on the bottom, so it cancels. Liters on the bottom, here it's on the top, so liters cancels. K is on the top, K is on the bottom, so K cancels. The only thing left is ATM. ATM is a unit of pressure, so that makes sense for pi. So now we multiply everything. Now we focus on sig figs. I have 2 here. That has 3, that has 3, but because of the 2, I'm going to have to round it off. 84 ATM. Now, you might remember that we did a lab in Chem A where the pressure was just under 1 ATM. So 84 ATM is pretty high. But think about it, when people do a dehydration process or curing, generally they put it in like sort of like a pressure cooker kind of thing. So higher temperature or higher pressure, that would get you to prevent that osmosis from happening. And if you didn't want it to be at such a high temperature, high pressure, you could reduce the temperature, right? If the temperature was lower, the pressure would be lower because they are directly related. But that's an example of using osmotic pressure for something that has a connection in the world. But generally, you need to have molarity, the R constant, and times it by temperature to figure out how much pressure is needed to prevent osmosis. Go ahead and do a level 2 question. Feel free to make up a question about osmotic pressure. That would be fine. Or something about vapor pressure lowering, any of those kinds of things. Okay, I have one more set of colligative properties I want to talk about, and they both have to do with changing state. So we're going to do boiling point elevation and then also something about melting point. So the third colligative property we want to talk about is boiling point elevation. So first of all, we just need to figure out what this means. Well, elevation is higher, right? Like how high something is. So boiling point is being higher than normal. So boiling point of elevation means that if you are trying to boil a solution, it will always boil at a higher boiling point than a pure solvent. Let's think about why that is. So remember that you've dissolved something in your solvent, and that's what creates a solution. So then also think about what that did to vapor pressure. So we said there was going to be less vapor pressure because remember the solvent is attracted to the solute. Well, if there's less vapor pressure, there's less stuff that can break through the atmosphere pressure and cause something to boil. And so what you need to do is you need to break the intermolecular forces. Remember that was from the end of unit 9. So the solute and the solvent are attracted between those different molecules. You have to break that attraction to get enough vapor pressure so that the vapor pressure can break through the atmospheric pressure and start to boil. Well, that just takes a lot more energy. So the boiling point elevation or boiling point will always be higher. It'll be elevated of a solution compared to a pure solvent. The other one I want to talk about is freezing point. Now, it turns out that freezing point will always be depressed or lower. So freezing point depression means that, okay, if you have a solution, the freezing point will be at a lower temperature than a pure solvent. Okay, well, this is not really as much about vapor pressure. There's got to be something else going on. Now, we might still think about the fact that the solvent is attracted to the solute. That's still true. So why might that affect the freezing point? Well, think about this. The solvent is not wanting to be attracted to the other solvent. And that's what has to happen for something to freeze, right? You have to create that structure, that organization where particles are attracted to each other. But because the solvent is also attracted to the solute, you have to remove more energy to get that solvent to stop rolling around. Because right now it's rolling around with the solute, not just attracted to other solvent particles. So you have to remove more energy so that the particles of the solvent are attracted enough so that they stop rolling around. So again, the boiling point will always be higher for a solution and the freezing point will always be lower for a solution. Now, let's quantify that. So if we're talking about a non-electrolyte solution, so this would be a solution that probably has a molecule as the solute, and so it would not conduct electricity. Here's the equation. Remember that this symbol means change. So the change of temperature boiling equals something called K for boiling times little m. Okay, so then that means that the boiling point of a solution is equal to the boiling point of the pure solvent plus the change of that temperature boiling. So remember that the solution is always higher than the solvent, so you have to add however much it changed by. All right, there's the same equation for freezing. So the change of temperature freezing equals to something called K for freezing, again, times little m. Okay, so the freezing point of a solution, remember, is always lower than the solvent. So you find the freezing point of the original solvent minus your change of temperature. So that's the idea. Okay, let's make sure we know what everything stands for. K values are constants. Somebody figured them out and now we can just use them depending on what your solvent is. Because we use water so much, I'm just going to give you the water constant K values for your notes. So the K value for water, so this is what it means. For every 1 molality, you will get an increase of 0.512 degrees Celsius for water. So if you dissolve something in water, so water would be your pure solvent, you're going to get a change of 0.512 Celsius for every 1 molality of that solution. And your K value says you're going to get a change of 1.8 kF, 1.86 degrees Celsius for every 1 molality. So then again, just review, M is molality. Okay, and then remember, molality is moles per kilogram of solvent. So remember, not the whole solution, just the solvent. So now that we've got what everything stands for, let's go back to this. So the change of temperature depends on what solvent are you using, because that'll change the K value, and how concentrated is your solution. So what is the molality? So the idea here would be if you had a higher molality, you're going to get a bigger change. Well, that makes sense because of the stuff that we said. More attractions between the solute and the solvent, because there's a higher molality, will give you a bigger change of your temperature boiling or your temperature freezing. It's important to realize that when you use this equation, that's not the new temperature, it's just the change of temperature, all right? So if you figured this calculation out and you ended up with something like 6, that's not boiling at 6, it changed by 6 degrees. So whatever your original boiling point one is now 6 degrees higher. That's an important little mistake that sometimes people make. Okay, I said that was for non-electrolytes. Well, what if it's an electrolyte? Well, remember, the only thing that changes with an electrolyte is now that you have ions floating around. So notice that that's the only thing that changes for the two equations. It's still the change of temperature boiling equals the K for boiling times molality, but now there's this little I. Now, you could think of it for the non-electrolyte equation, this I value is just 1 because there's just one particle floating around if you dissolve a molecule. But if you have ions floating around, so that's what I stands for. And just a little side note, oftentimes that I is referring to as the Van 't Hoff factor. So if you hear that, it's just saying how many ions are floating around because of whatever your solute was. So let's just make sure that makes sense. Let's do a couple examples. Imagine you had this compound, aluminum chloride. how many ions would be floating around? So you're asking yourself how many positive pieces would there be and how many negative pieces would there be? Well, the positive piece is aluminum and there's only one of them. So there'd be one positive piece. The chlorine is the negative piece, but there's three of them. There's a -1 3 times. So that means that you have one aluminum and then 3 chlorines. So total you have 4 ions. So if you were figuring out the boiling point of a solution made with aluminum chloride, you would still use whatever the K value was for the solvent, whatever the molality was, but then you would times it by 4. So you get even more of a change of temperature with electrolytes because there's even more attraction happening because now there's so many ions. And then here's just another one. How about sodium sulfate? Now, again, you're counting the positive and negative pieces. So the positive piece is sodium, and there's 2 of them, a +1 and another +1. So that's 2. But the negative piece is this whole SO4, sulfate. So the sulfur and the oxygen don't split apart into ions. There's 1 sulfate and 2 sodiums. So then that would be 3 different ions floating around. And again, the reason this matters is because it's showing you that there would be more of a change of temperature if you had an ionic compound because there's even more attraction happening that affects the solvent. And so that's why that could be important. Okay, so I just gave you a whole bunch of new equations. Well, what do we do with that? So let's use boiling point elevation or freezing point depression to do something interesting in the chemistry world. And it turns out that we can figure out the molar mass of something. So this is what it would look like. Imagine you were a lab technician and somebody brought you an unknown compound X. And what you did is you created a solution. You took 5 grams of that unknown X and you dissolved it in 60 grams of water. And you first check to make sure that it did not conduct electricity, because if it does conduct electricity, that would change our equation and that affects what we need to do. So you found out that this solution that you made did not conduct electricity and you froze it. And when it finally froze, it was -1 degree Celsius. From that information, we can actually figure out the molar mass. And then once you know the molar mass, you can figure out the identity, which could be really useful in a forensics case or just a curious thing that was happening in someone's home or found in the corner somewhere for a contamination. So identifying the molar mass could help us identify the compound, which could be really cool. Well, here's the 4 steps we're going to use to solve. First, we're going to find the change of temperature because we want to know something related to molar mass. And the definition of molar mass is grams over moles. Well, I know my grams, but I don't know moles. But the freezing thing is related to the new equation that we just learned, which has molality in it. So I know that if I figure out how much it changes by, I can use this equation to eventually figure out moles. That's where I'm going with this. So the change of temperature is the original definition minus the new temperature, right? So it used to freeze at 0 degrees. That's what water freezes at. And now it's freezing at -1. So the change is just 1. Now, obviously you could do that in your head also, but here's the idea. So the original temperature minus the new temperature gives you the change. So 0 minus a -1 gives you a change of 1 degree Celsius. Well, now I can plug that into the new equation that I just got today, which was delta T equals Kf, because we're freezing, times molality. All right. Well, 1.0 grams was my change of temperature. I just figured that out here. 1.86 is my K value for water. I gave that to you on one of the previous slides. And remember, that's degrees Celsius per molality. And then I can solve for molality. So question mark molality is what I'm looking for, because if I divide 1 by 1.86, degrees Celsius will cancel. I'll be left with molality, which is what I'm looking for. So go ahead and do that math really quick, some algebra. 1 divided by 1.86 gives me this number, 0.5376. Don't worry about sig figs, just leave it in your calculator. But that is the moles per kilogram. Well, the problem is that molar mass is just the grams per 1 mole. Well, this is the moles per 1 kilogram, and I didn't have a full kilogram. I only had 60 grams of water. So the next step, so there's 4 steps. So step 1 was finding the change of temperature. Step 2 is using the change of temperature equation to find molality. Now we need to find the moles of X if in just 60 grams, because this is 1 kilogram. Okay, so here's my setup. 60 grams of water. I change that into kilograms by dividing by 1,000 grams. I multiply that by my molality, because then look, kilograms of water will cancel and I'll be left with moles as my unit. I multiply everything on the top, divide everything on the bottom, will give me this number. And again, just leave this in your calculator. Don't do any sig figs yet. All right, so now this is my number of moles. But remember, I'm trying to find the molar mass because that's related to the identity. This number of moles, you could get that in any way. So what's the molar mass? Well, molar mass is grams divided by moles. I have grams of my unknown. I have moles of my unknown because of all of this work. So now I can find the molar mass. 5 grams of X divided by my 0.032258, whatever, moles of X. Divide that out. That will give you your grams per mole. So then now as a lab technician, as a chemist, I could look in a database of which compounds in the world have a molar mass of 155 grams per mole. And then I could use observations and other properties to match it and figure out the identity. So kind of a bunch of little steps, but practice this in the unit practice problems today to kind of see this. And then this is actually also what our lab is going to be about in this unit. All right, well, go ahead and process what just happened, write a level 3 question, and then also do a summary related to all or any of this colligative property kinds of stuff. And again, feel free to watch back this example again if you need to, or do the unit practice problems to see more examples like this. And that brings us to the end of day 4. So here's the things I want you to do before our next session. Go back and finish any cost of questions or summary if you didn't already do that. And then your solutions practice from day 1 and 2, remember that should be done. So you should submit it if it's done. If you have any questions, let me know. Also, that concentration FET lab should be done. So if it's done, go ahead and submit it. If it's not done, finish it. Let me know if you have any questions. And then I highly recommend you do the unit practice problems for today because there's no new assignment. So the only way you're going to know that if this stuff really made sense is if you do some of those practice problems. Even if you don't write them down, but you just look at them and think about the answers and then look up the answers, that counts as practice. So that would be fine. Or you could actually work them out through and then check your answers. That's a good idea too. All right, that brings us to the end of today. We'll see you at our next Zoom meeting. Thanks so much for joining in. Goodbye.